Going a little bit deeper into this, here we have a manifold. So it's something. Let's say, temperatures, pressure, three-dimensional position, like in some place, let's say Chicago. So there's a bunch of numbers, and they typically have some reasonable ranges. So you don't inspect temperatures in Chicago to drop to millikelvin, and you don't want them to be much higher than hundreds or 1,000 Kelvin. So state space typically tends to have finite range in various directions. It's a manifold. You cannot be outside of it because that is not an option. And what happens there is that you pick a state, and in fluid dynamics, people tend to call such a thing a representative point. So much that I'm explaining today, if you want a geometric picture, you can think of fluid that's moving, and you put a particle in it, a tracer, and you see what happens to it. And the tracer will have a property: the fluid is not supposed to destroy it or create two tracers out of it. So there'll be some conservation. And that's a property of all this kind of dynamical systems we'll discuss together today, ones which are continuous. So if you have a law of evolution in time, what will happen to this point, it'll follow the instructions of the law, and it'll trace out trajectory. So we are within the football field, we are running around doing a trajectory that's possible. And the law, if it's deterministic, has a property that I will end up on unique place. And if I can specify my state, which is a bunch of numbers, you can think of the vector, but the manifold is not necessarily a linear vector space. So it's just an array of numbers, d of them. Now, if you go to Howie, third or fifth floor, d is actually infinity because people there study fluids, and the fluid consists of infinitely small, material elements in Navier-Stokes or Eulerian idealization. And it turns out it's okay. It's easy for us to understand finite dimensional systems, but it's actually possible to do infinite dimensional one. So here we are in a manifold, and we are tracing out an orbit following instruction set F. By trajectory in this book, we will always mean something that's finite in extent, part of evolution of the system. I will explain in a moment why.